on slide 11 of the ideal gas law slides. There is a problem where it's asking you to come up with the density of a gas. The problem with this is that, with the problem when you first look at this, is that it looks as though you don't have enough data. So I've mentioned in the slides, you have to take one of two approaches. Either approach will get you to the same endpoint, but slightly different route to get there. I don't know that there's necessarily one way that's easier than the other. So I'm just going to quickly show you one of the approaches, and perhaps if you try the other, you can get yourself to the same density. So we're going to be using the PV equals nRT formula. Off to the side, I'm just going to mention that they've given us the pressure at 126.63 kPa, and they've given us the temperature as 12 degrees Celsius, but we have to add, of course, the 273 to that, so that gives us 285 Kelvin. So remember, we always have the ideal gas constant, kPa times liters over Kelvin times moles, but in this case we have two variables with nothing in there. So here's the beauty of it: you can make an assumption in each case. You can assume you're dealing with 1 liter and then solve for moles, or you can assume you're dealing with 1 mole and solve for the number of liters. Again, either way will get you to the same point. The other thing I'm going to mention just before we move on any further is the density of anything, remember, is the mass over the volume of that material. Okay, so I'll do the first approach. It says to assume 1 liter. Let's assume we're dealing with 1 liter, and we're going to solve for a number of moles. So, excuse me while I kind of shift everything over here on the fly. It's going to be PV over RT, and as we plug in, it's going to be 126.63 kPa times 1 liter. That's some easy math, all over top of 8.31, and sorry, I'm going to avoid the units at this time, all over 285. So as I bring in my calculator, we're going to be going 126.63 times 1. I'm not going to bother. Divide by 8.31 times 285. That leaves me with number of moles of 0.0535 moles. Now, of course, moles isn't useful in this equation. Right? You need mass and volume. We've already got volume. The beauty of assuming 1 liter is that that's your volume you're going to put in. One other piece of information we haven't used yet tells us we're dealing with pure nitrogen gas. And remember, nitrogen is one of our diatomic molecules, has formula N2, and therefore if you go to your periodic table, it's going to be 28.02 grams per mole. So let's take our moles, convert it into mass, plug it into our density formula, figure out the density. So I'm just going to say mass of nitrogen is going to be moles times the molar mass, and it's 0.0535 moles times 28.02 grams per mole. Moles will cancel, leave you with the mass, so that kind of confirms we're doing the right thing here. I'm going to leave that number in my calculator and times it by 28.02, and I end up with 1. When I round that, I'll go to 1.50 grams. This can be put up into our equation. 1.50 grams over 1 liter. Again, I'm getting that 1 liter from the value I assumed, and you don't need your calculator there. That means your density of nitrogen gas is about 1.5 grams per liter. Now again, if you go back and use this other approach where you substitute in a number of moles, you'll be solving for a volume. And again, if you assumed 1 mole, you would have the molar mass of nitrogen already calculated, and you'll just have a volume you'll have to divide by. Either way, it should get you to 1.5 grams per liter. So have a try at that and see which way you prefer.